Hi everyone, my name is Nick Souter. I'm a researcher at the University of Sussex. I'm working with Charlotte Ray on a project focusing on reducing the carbon footprint of MRI analysis and data processing. Today I'll be talking about some work we've been doing on this, as well as some tools and recommendation for making your research computing greener. This has been born largely out of conversations with the OHBM Sustainability and Environmental Action Special Interest Group, or CSIG, so please do look up CSIG if you're interested in getting in touch. Sorry not to be able to join in person today, given that this is a sustainability themed session. It didn't feel right to make the flight out from the UK to Canada, but I'm really happy to be able to share this work with you all the same. So this is a figure from Charlotte and some colleagues in a paper last year focusing on ways that neuroscientists can reduce their carbon footprint. You'll have heard about some of this today, I'm sure, about things about flying less and recycling liquid helium for MRI scanning. We're focusing specifically on this aspect, compute carefully. Basically, when you're analysing and processing data, try and do it in a more environmentally sustainable way. The impact of data processing and the climate crisis isn't often talked about, but it is a pretty big factor. So by some estimates, the IT sector accounted for 2 to 6% of global CO2 emissions in 2020. And as we use more and more data, this is projected to increase up to 20% by 2030. And 2 to 6% in itself is a pretty big chunk when you consider that that outweighs the contributions of aviation and shipping by some estimates. And this is all relevant to neuroscience and neuroimaging in particular, given that we often rely on large data sets and computationally expensive analysis to answer our questions. So we're working on a paper at the moment, providing some top tips for sustainable research computing in neuroimaging. I'll talk more about most of these towards the end of the presentation, but for the bulk I'm going to be focusing on 4 tips that kind of sit in the middle of the data analysis lifecycle. So first off, tracking emissions. So given the impact of data processing on carbon emissions, several tools have been developed to try and quantify this impact in research. So one is green algorithms. This is an online calculator that allows you to input aspects like CPU usage and runtime and hardware, and then spits out estimates of carbon emissions. This also provides a server-side tool that can be built into high-performance clusters, which basically uses logs to retroactively estimate your carbon emissions. Then tools like Carbon Tracker and Code Carbon are embedded packages which can be built into specific programs, and then again provide estimates of emissions based on your energy usage. Luckily for us, Code Carbon has recently been integrated into fMRI Prep, a pre-processing pipeline. That's motivated this pre-registered study that we're running at the moment, which we're currently entitling Measuring and Reducing the Carbon Footprint of fMRI Pre-Processing in fMRI Prep. And this relates to our green tip of pre-processing conservatively. So we're interested in data pre-processing in fMRI because this is a particularly long and computationally expensive step. For some subjects it can take over 24 hours to run, depending on the amount of data that you have. This includes a number of steps like registration, temporal filtering, motion correction, all of this that really adds up. So there is potential scope here for reducing the energy usage and therefore emissions from this aspect of the process. We're particularly interested in fMRI Prep, which is an optimally combined package that takes elements of pre-processing from different sources and combines them together. Because this gives us the option to toggle on and off various different options, as well as parametrically vary some of them, and therefore quantify the effect that different parameters have on carbon emissions. And again, Code Carbon has been integrated to fMRI Prep now, so you can just toggle on this track carbon and code country flag, and at the end fMRI Prep will give you estimates of emissions for each subject in your data set. So we'll be running 10 different pipelines of fMRI Prep with various different settings, so we can look at the effect of each on carbon emissions. We're using existing data from a previous data source from Gorgolewski et al. 2017. This is one run of a stop signal task from 257 subjects that was initially used in the validation of fMRI Prep by Esteban et al. So this will include a baseline pipeline with everything just running as default. One where we disable the default setting of free surface reconstruction. One where we run this sloppy testing mode where we kind of cut corners on registration. That's typically used for kind of testing. One where we implement this low memory flag, which tries to reduce the memory usage of fMRI prep. One that increases parallelization, up from a default of 5 to a value of 16, basically spreading the job over more computational resources and hopefully making it run more efficiently. One where we're increasing the resolution of our output volumetric space to produce higher quality data. One where we're adding a surface space on top of our default volumetric space. One where we're removing parallelization altogether, down from a value of 5 to a value of 1, so probably making things run less efficiently. One where we're implementing aroma, so the automatic removal of motion artifacts. And finally implementing fMRI Prep's in-house field map-free distortion correction technique. So we'll be able to measure the carbon footprint of each of these different packages and then compare them to our baseline pipeline. So again, Code Carbon spits out a number of metrics, including the duration of compute, the estimated emissions in kilograms, and then the energy usage of CPU and RAM. An important caveat here, we found that on our particular architecture here at Sussex, Code Carbon for fMRI Prep appears to be kind of contaminated by energy use from other jobs happening on the same node but outside of fMRI Prep, which basically means we're not getting an accurate summary and it's overinflating estimates of emissions. So Code Carbon works brilliantly if you're using it in hardware isolation, so using an entire node for yourself or on your own machine. But for our purposes, we've had to use an alternative technique where we're using kind of a green algorithms approach of estimating carbon emissions based on high-performance computing logs retroactively. And I'm happy to talk about this more if anyone's interested in getting in touch afterwards. As well as measuring the emissions of our pipelines, it's important for us to make sure that they're doing good pre-processing. And for this, we're using a method that's similar to something used by Esteban et al. In the original fMRI Prep validation. And that's to quantify task activation in regions relevant to our task. So specifically, we're going to be looking at the post-central gyrus for motor activation and the pre-supplementary motor area for response inhibition. Using feat query and FSL, we'll look at height of activation for each subject in each of these regions for each of our pipelines. Obviously, there's no ground truth with task activation, but in a task as robust and reliable enough as a stop signal task, we can basically expect that a pipeline that produces good quality data, a pipeline that produces high sensitivity to task activation has just done a good job at uncovering that expected activation. So we don't have the full data yet, unfortunately, and we don't have any statistical analysis, but what I can do is tell you the story so far. We've run 4 pipelines so far. On the y-axis on the left here, we've got mean task activation in the post-central gyrus and the pre-supplementary motor area in our solid red lines here, and then carbon emissions on the other y-axis in our dotted green line. First of all, relative to baseline, we see that disabling the default free surface reconstruction appears to reduce estimated carbon emissions by a huge 50% while having really no negative impact on sensitivity to task activation. So if you don't have a specific reason to be running surface reconstruction, this could be an easy step to make your pre-processing more sustainable. Implementing our sloppy testing mode appears to again significantly reduce task activation sensitivity as we'd expect, and also to reduce emissions. So this isn't one we'd recommend for actual pre-processing, but something that could be useful in kind of a testing mode when you're figuring out exactly how the pipeline runs. Then this low memory flag unfortunately doesn't appear to have any impact on carbon emissions, and as we expected also has no impact at all on task activation. So again, we don't have the full data yet, but when we do, we'll be able to run statistical analysis and find kind of the sweet spot of pipelines that reduce emissions drastically while having no impact on data quality, and we'll be able to make some recommendations on this basis. Another tip that's come out of this project is to tidy up junk files. So this on the right here is the proportion of files generated by our baseline pipeline that either we intend to use in subsequent analysis in any way, and then junk files either in the working directory or the output folder that we don't have any intention to use. And we can see that the files we're interested in only make up 4% of the kind of the whole size of the data we produce. This is relevant because unnecessary data storage can increase the workload of servers and increase the need to air condition them, as well as increasing the rate of hardware procurement when servers fill up. So if you can regularly delete these files, in this way you're reducing your footprint as well. For this purpose, we're currently working on a script that should automatically run through and delete junk files for fMRI Prep. This isn't yet available, but do keep an eye out for it. It's going to be coming soon. Another tip that I'll touch on, just because we've got some concrete data for it, is the effect of time and location on the footprint of your computing. So here we're talking about carbon intensity, which is basically for the energy you're using, how much carbon is being emitted. And this is going to vary depending on your access to renewable energy sources in a given country. Here we've got public data for the UK National Energy Grid. We've got carbon intensity up on the y-axis, and we're looking within each year back to 2017. We're looking at, for example, mean carbon intensity at 12 PM on a Monday within that year, or 4 AM on a Wednesday within that year. And in doing this, we can see some very predictable patterns of carbon intensity. So with intensity peaking at around 8 AM and again around 6 PM and 7 PM. This being times of peak usage when people are watching TV, putting the kettle on, starting to cook dinner, whatever that might be. And then a lull around the middle of the day and again in the middle of the night when usage decreases. So if you can schedule analysis and pre-processing to run at times of particularly low carbon intensity, you can use the same amount of energy while having a smaller carbon footprint. And tools are currently in development to try and provide the option to schedule analysis in this way. So do keep an eye out for that. But carbon intensity also varies by country, and this is because different countries will use a different mix of renewable and more fossil fuel intensive energy sources. So we can see, for example, that Iceland has a carbon intensity about 0.01% of South Africa. This is because Iceland is relying largely on renewable sources like geothermal energy, while South Africa relies on more fossil fuel heavy sources like coal. So one thing you can do is prioritize cloud computing services on the basis of carbon intensity between countries. This does have some problematic kind of social and economic implications in terms of disadvantaging economies that don't have access to renewable sources. So it's not an easy, simple tip, but it is something you can consider when comparing different cloud computing services. Just out of interest, this top arrow here, we've got the UK where I am, and then slightly further down we've got Canada, which is pretty well on green energy thanks to reliance on hydroelectric energy. But we also see massive variation within countries. So this is states within the US, and we can see that Vermont here has carbon intensity about 1.5% that of Wyoming. And then again within Canada, we see that the carbon intensity in Quebec is about 0.2% of that in Nunavut. So even when prioritizing different providers within countries, there's quite a lot of scope to prioritize based on carbon intensity information. So to finish, I'm just going to go over our top tips in a little more detail, as there's some that I haven't been able to cover here. So first, you can make your computing greener by using existing data. The reason here being that you're avoiding energy associated with additional scanning, but if you're using pre-processed data, you're also reducing the need to pre-process it yourself, which is going to save on computing, as we've seen. You can plan and pre-register your analysis. The idea here being that if you have a good plan of exactly what you're going to do and what options you're going to use beforehand, you're less likely to have to unnecessarily repeat stuff and therefore use unnecessary energy. Even when you have pre-registered stuff and you're at the stage of analysis, it can be useful to try running everything on just one subject first, just to make sure everything runs without bugging before you send it to the whole sample. As we've said, you can track your emissions to try and quantify and understand your impact. You can pre-process conservatively, as we've said, and we'll have some concrete data to show on this point soon. Again, time and location matters, and you can prioritize based on carbon intensity data. Again, you can tidy up junk files to reduce workload on servers. For data that you are going to keep that isn't junk, you can plan how long you're going to keep it and where you're going to keep it. It may be that after a certain point, data is fine to be deleted, and again, that will decrease pressure on servers. When uploading data to data repositories, you can try and use those that are more environmentally sustainable, that use more renewable sources. You'll never have a perfect source, but this is something you can consider. When you are sharing this data, you can reflect on exactly what needs to be shared. Sometimes it might be the case that you can share just pre-processed data that's enough to replicate your analysis and keep you accountable, while not sharing all raw data, which is going to be much larger in size. And finally, as we're doing today, you can talk about green computing just to make this issue less neglected within the neuroimaging community and the neuroscience community. Yeah, it's a good form of just making this a less neglected issue. For the sake of the recording, here's the references from today quickly. And finally, just thank you for listening and for your time. You can contact me at any of these channels here. Shout out again to the OHBM Sustainability and Environmental Action Special Interest Group and CSIG. Please do contact them via these socials and give them a Google to check out their work and get in touch. And finally, thank you to all my collaborators on this work that have helped on both the top tips and the fMRI project. Thank you very much.